Okay. Hi, everyone. Thank you so much for joining. If you're new here, my name is Claudia, and we're HelioHub, a Discord community for undergrads and recent grads interested in heliophysics. We're funded by the NASA Coffee's Drive Center, and I'm joined here by my wonderful team, Phoebe and Dan. Um, just a little reminder, if you have any questions during this webinar, please feel free to use the Q&A function and we'll try to answer those. And finally, I'm excited to introduce Jeremy McCauley, an aerospace manager at the UC Berkeley Space Sciences Laboratory with over 30 years of experience. At SSL, he leads the mechanical design of flight hardware and mechanisms, supervises engineering and facilities teams, and manages projects while supporting overall systems engineering. In this webinar, he will discuss key space weather considerations in spacecraft and instrument design and how engineers account for the harsh space environment. Please join me in giving a warm welcome to Jeremy McCauley.
All right, hi everybody. Welcome. Glad you're here. Glad I'm here. It's good to be a part of this, and I'm looking forward to presenting and then also hearing your questions and answering as many of those as I can. As was stated, I'm talking about space weather considerations for instrument and spacecraft designs. My background's mechanical, so 99% of what I talk about will be mechanical engineering. It's just the way that I look at the problems that I'm dealing with. So they have wide-ranging ramifications, but it still ends up coming back to that in my heart. That's the way that my mind thinks through the problems that I have. Um, there it goes. Like she said, I have been here since 1994, so I've got 32 years at the Space Sciences Laboratory on and off. I do have a couple other things that I run around and do, so it's not the only thing I do. But in that time, I've had some phenomenal opportunities, including being at the vehicle assembly building when the space shuttle rolled out. Those of you who are saying space what? Space shuttle is how we used to get astronauts into space. It's a really neat opportunity. That was actually the second to the last launch, and so it was fun to be able to be there. Got offered an option of going in and riding out on the crawler. It's an 8 hour ride to go the 4 miles that they go. So we actually decided that we would pass and instead watch from afar. But that was one of the neat opportunities that I've gotten. And here's me more recently working in a clean room building the Lucy Night instrument. You can see a smattering of the missions that I've worked on there, some of the names that you may not have or may have heard of because these are big enough to be in the news. But Solar Probe is in the mission in the middle. That's one that's much more common. And then Escapade is one of our current missions that's flying on its way to Mars. Working with the Rocket Lab bus, we're doing some heroic orbital maneuvers to make sure we can get there in a timely manner and make that all work on the budget that NASA gave us. Lucy Light and Lucy Night are the next two missions that I've just completed. Those are both going to the lunar surface in the next couple of years. That'll come in later as we talk about space weather, but those are some fascinating places that we can draw. I can draw a bunch of experience for and talk through. I do have a whole bunch of different roles that put me in this place. My background is mechanical engineering, but that led me through when you're trying to work in mechanical engineering, contamination gets to be a major concern. Again, we'll talk about this more as we get into space weather, but because of the concern coming into other job duties for my mechanical side, I ended up taking on the responsibilities of learning how to do contamination engineering, planetary protection, and looking at what does that take. So I fulfill that role as well. Also worked on integration and test management and project management, just depending on what's needed. I try to fill the roles wherever they are and make sure that everything works as best I can as we're going. My main role and the main thing that I do is build deployable mechanisms. So I build things that actually move on a spacecraft. It's really exciting. It's fun, slightly terrifying when you're waiting to see if they actually worked correctly, because one of the things that makes mechanisms really interesting is if they don't work, the spacecraft could be thrown off of balance. You could actually have problems. And so those are things that I enjoy the challenge of, I enjoy the implementation of, but it's also one of those fascinating things that has to work right the next time you press it. Some other items that we'll get into is thermal isolation, structures, electronics enclosures, and sensors in general that come along with those mechanisms and the pieces that you're building as I put things together. Things I won't be talking about, and this is kind of a funny start, but I was trying to get into what, when you think of space weather and we think of weather here on our planet, there's things that we deal with all the time. And most of the time when I go in and I'm looking for materials and I'm trying to figure out whether they will work well in space, the first thing that a vendor quotes me is a saltwater test. And it's funny because saltwater has an amazing ability to break things down on our planet, but I never encounter it. And so my considerations are very much different. That test actually has no bearing on what things will work with. Similarly, I don't ever deal with rain. The only times I've ever dealt with rain or salt water, it's because the unit crashed, and that's usually a bad thing. We don't want that to be the basics of how we work with or how we interact with our hardware. So those aren't the types of weather we're talking about. I also almost never deal with corrosion. If you think about rust, you think about oxidation. Again, it requires water and oxygen in close proximity, usually to cause something to happen. Those are just concerns I'm never going to run into in space. And so when we talk about space weather, we really are talking about a different subset of concerns and of material considerations that bring us back into design and make us look differently at what we're doing for space. Typical issues that we do deal with and standard environment that we have to run into is dealing with the vacuum environment of space. Space may not be a perfect vacuum, but it is something that will change the properties of your materials. The solar heat that we get, the sun is incredibly hot. Thankfully, it only fills a tiny amount of the sky, but it does become a major issue that we're always dealing with. Shadows of any type are an environment that I don't know if you can call it a problem. It's just a reality of what we have. And so we're always looking to see how we can use those and how we can, how they become a danger for us. Space is full of charged plasma, and so I put a picture in here just to kind of give that idea because it is one of the things that we don't always think of. When we think of space, we think of it being empty, but space actually has particles in it. And those particles are a lot of what I have to worry about and be concerned about. Now, they also are most of what justifies me being there. So if I'm going to run science, I'm measuring something. I need to have something there to be measured. And so the particles in the plasma actually are a large part of what we're out there for. And finally, radiation exposure is the other big one that I deal with. The Earth and our biosphere does an amazing job of protecting us. It's designed to do that and has the ability to protect life in such a clear way. And so when we get outside of that protective shield, there's a lot of different considerations that we deal with, and having to see how materials and also our electronics interact with the radiation and radiation exposure that they get is one of the things that we do. All right, so how do we address those? The simple things mechanically that we use to address those is the materials that we choose, the thermal design that we put together. Dealing with charging is what allows us to deal with the plasma and the particles around us, and then radiation isolation is what that word should say, and is how we deal with isolation or how we deal with radiation. Looking at materials. Materials is a fascinating way, exposure that we have to deal with as we're designing something. The struggle that I have with materials is many materials that we think are the best materials that we could possibly use here on Earth don't work well in space. And so there are many different pieces about handling and oxidation and particulating that come to us. Half of the time, because we're building a scientific satellite, we don't want anything magnetic. We're almost always going to have magnetometer on board. And one of the best things we learn in contamination control is all of the contamination that is with me in space is usually because I brought it, whether it's particles, chemicals, magnetic fields, so much of that, or electromagnetic interference, so much of that is brought by the spacecraft itself. So the first thing that happens is I throw out all magnetic materials once I have a magnetometer on board. To do that, I lose steel, which is a basic material that we use for building almost everything on our planet. And so I'm very quickly brought to other materials. I can only use certain stainless steels. I can use aluminum very well. And then I have plastics, and plastics, there are very, very different numbers of plastics that actually do well and deal with the harsh environments of space. First of all, one of the things when, especially when we're dealing with plastics, which we're engineering on a daily basis, plastics don't always deal well with vacuum. So vacuum has a tendency to pull whatever water molecules are deep inside of the plastic out of it. They also can tend to pull unfinished byproducts from the reaction that made the plastic. So typically plastics are a chemical reaction that firms and solidifies after it's mixed together. And so you can find that there's unfinished polymers or half of the chain that's not well bonded, and those will actually be pulled out in the vacuum environment of space. And when that happens, that mass is lost, but also properties are lost in the material because you can end up with voids and you can end up with very small subatomic problems happening. So I put a picture that I thought was just fascinating. This is a POM tube or palm tube, and that's it's a type of plastic that we consider and don't always use. But you can see it has been actually irradiated to a point where it's got cracking on the outside, and we can think, oh, that's not such a big deal until we look at the second picture, and you can see that the cracks on the outside of this material are penetrating 2 and 3 millimeters deep into the cavity inside of the tube. And so what is happening isn't just a surface reaction. It's not just a loss of a few properties. We're actually watching the material come apart and lose the ability that it has to maintain strength and to maintain its own performance in whatever situation that we have. On the good side, there are several plastics that work well. My favorite right now is called Ultem. Ultem is a thermoplastic that's put together and then deals with vacuum incredibly well. And because it's plastic, it tends to be thermally isolating. So as we get to thermal control, which we'll come to, we will we will start talking about the isolation that we can get and whether or not it's useful and how it's useful. Radiation also can damage our plastics or the materials that we use. And so it's another concern that we have. Most of the time, what we'll see this used in is from a radiation standpoint, we'll irradiate electronics and see what happens to them. But NASA also does an amazing job of sending up samples of materials. And so this bottom picture is actually is the same sample at different times of oxygen, and what they're trying to do is do atomic oxygen and space exposure. And so NASA takes up just a rack of materials, sits it on the outside of the space station, and a year or so later, they'll bring it back and they'll look at the exact same piece of material and say, hey, those don't look the same. What happened to it? Is it working? Is it still maintaining its structural ability, even though it's the color of it has changed? Um, Fun things. This is what actually makes it difficult to send like your iPhone camera into space and use it as a spacecraft because that gets suggested all the time. iPhones are cheap. Why don't we just throw them into space and use them as spacecraft? Well, it happens that most commercial camera systems, their lenses degrade in the UV of space, and so they get dark, which of course ruins the point of having a great camera. You can also see some of these have torn and actually broken through the material. And so NASA keeps track of that. They actually, can do studies on this. We can't irradiate on the planet. We can actually send things out and have them bombarded and see what the behavior is on a particular piece of material or on a coating. If we're worried that the paint or the metallic coating that we put on is going to peel, we can test that. So radiation becomes something that we always want to keep an eye on and make sure that whatever our exposure is, we're using the right materials so that they survive it. The other one, like I said, is that when a material is exposed to vacuum, it actually breaks down. You can often lose polymers or you can lose chemicals inside of it that aren't well bonded. And so that we call that outgassing. And the nice part here, NASA maintains an outgassing database. They will also test particles or test materials to make sure that they're not outgassing. But you can imagine if I had a material, say a chunk of plastic that I put in, and I used it to hold a sensitive mirror or an optical system. And as I send it out, it gets into vacuum, and some percentage of that, let's say 3 or 10% of that plastic actually comes out and deposits somewhere else on the instrument. Well, you don't get to control where it deposits. So it could deposit back onto your optics. It can deposit on your detectors. Some of the most interesting ones, the metal cadmium actually vaporizes off of materials. So if we had something made of cadmium or with cadmium plating on it, many of the connectors that you use in commercial electronics have cadmium plating on them. It's a standard thing. It's great for conductivity, so people thought it would be really good to use in space, but it vaporizes, and that conductive material comes off of the metallic conductor you want it on, and it deposits on something else, often something non-conductive, which means all of a sudden you've taken a conductive surface and you've actually produced a short. So the NASA outgassing database helps us with these kinds of things. It keeps us aware if we run across materials that are doing weird things, and keeps us alert to making sure we don't reuse materials that somebody else already had to learn. One of the fun things about materials that I have to deal with, and again, this will come back up, the fun thing about these is that they come back up over and over again. There's options and choices that you make, but I may need the outside of this material or the inside of this material to be conductive. So one of the things I never want to have on a electromagnetic sensing platform is an isolated conductor, and that's because that conductor could charge up and then it could actually discharge across the isolators that are around it. And that discharge will show up as a scientific signal, something that actually ruins what we're trying to get. So a lot of the issues that we're coming into are trying to protect the science that we're getting. And that's where that becomes an issue. We can coat that. We can put the plastics that are isolating it. We can coat them so that we actually dissipate that electricity. It never becomes a charged issue. But that is one of the questions we come into. The next thing that I can mitigate, and that I design consideration that I have the ability to control, is my thermal design. And thermal becomes a major issue for us because, like I said, we always have, or almost always have, a view of the hot sun. And the hot sun is giving us roughly 1,400 watts per meter squared. That, we notice what that's like when we sit out on the beach, but in space, there's no cooling breeze, no water, nothing else to cool us down, no air to convect that away. So I have to deal completely with that heat. And you can see here, this is a great first picture of Solar Probe. And Solar Probe is the first spacecraft to go within 10 solar radii of the sun. And it is there. It is in an orbit that puts it there now every couple of months. It gets that close. That also makes it the fastest man-made object ever made, uh, close to 500,000 meters per second. Pretty impressive to watch and see it go. But you can see really quickly that facing the sun is this bright white portion. And the thermal design of Solar Probe, in order to get that close to the sun, we have to shield entirely from the sun's rays. There's so much heat there that what there is there's a 4-inch carbon-carbon composite shield that radiate or that literally ablates and burns off as it's being used, but keeps all of the heat away from our spacecraft. And everything is hidden inside the shadow of that protective case. There are only a few things that actually stick out outside of that. One is the tips of the solar arrays. When we're closest approach, the solar arrays tip back. I actually have a version of them tipped out. This is when it's far away, like at Venus or at Earth. And then these arrays tip back and they align back so that only a portion of them is exposed to create electricity. Because of how much sun we get there, that portion is enough to generate all the electricity the spacecraft needs. The other thing is there's a particle detector here, and then 4 antennas that protrude outside of the solar shield. And I got the privilege of working on those deployable antennas. They actually launched along the body of the spacecraft, and then once on orbit, we were able to deploy them out. And they sit out and they actually experience the sun in all of its radiant glory all the time. And so the heat that they experienced caused us to have to design into new materials. And so can't just use aluminum when your system is going to pass over 1,300 degrees centigrade. The aluminum will melt right off. And so those are fun because we actually got to explore new materials. And this is niobium, which is a rare earth metal that doesn't have terrible. Most of the rare earth metals happen to have incredibly high densities, and niobium steps down and is pretty close to the same as stainless steel. So it allows us to keep high heat high heat properties in a lightweight metal that actually can work in space. What makes that also work is, like I said, the sun may be incredibly hot, but as long as it's on this side of the solar shield, everything else is facing cold space. And cold space is at 3 Kelvin all the time, wherever we look at it. We have a great ability to radiate there as long as we can cut ourselves off. So one of the fun things is you're always looking for ways to eject heat into cold space. You never want to have to worry about not being able to do that. The most interesting environment I've ever had to deal with, interestingly enough, is not the solar probe environment where we're really close to the sun, because when we're really close to the sun, there's so much cold space to look at. The actual hardest one that I've had to do is dealing with the lunar surface. So these are pictures of Lucy night. I put three of them on here because it's kind of fun to see the different stages of this. This is Lucy Night in a correct picture. This is really close to sunup, but you can see that the backside of it is just thermally protected. There's solar arrays all the way around. This is going to be the sun side. It's going to come across here. There are antennas that deploy out that I got the privilege of designing those. And then this enclosure up here actually has our instrument in it. What happens on the lunar surface is the surface keeps you from being able to see cold space in 180 degrees. 2 pi uh, steradians of your view is blocked by the surface of the planet. That would be fine if it were close to outer space temperatures, but instead, it's really hot during the day and extremely cold at night. So the surface temperature of the moon is roughly the temperature of boiling water during the day, so 100 centigrade, and roughly the temperature of liquid nitrogen at night. So when you're building something, it doesn't have just one environment that you get to deal with. You actually have an environment where during the day, when you have all the power you want, you're too hot. And during the night, when you have very little limited power because there's no sun to provide solar energy, you're trying to stay warm. And so you're dissipating power to keep yourself hot. So inside of this box, we got to design an isolation system that would allow us to keep our electronics pretty much at room temperature all the time. So a 1 month long day on the moon, it takes 28 days for the sun to come up and go down and come back up again. We actually have about 10 or 20 centigrade. So it basically sits about the temperature of the room you're sitting in right now and will stay there all the time, no matter what happens outside and no matter how hot it gets or how cold it gets. So that was extremely challenging. What's fun about it is the way you can do that is you put a very nice radiator on it. And this picture I thought was really, really cute because, it's really nice to be able to see the radiator, which you can only do if the sun were in this position. But if the sun were in this position, our instrument would be melted. This is our radiator. It needs to eject into cold space. It can never point at the sun. And so that becomes a major issue for this picture. But it's definitely would be invisible if it were in the shadow. So doesn't work the other way. This is the one other environment that we have to deal with is actually the traveling to the moon. We get a completely different set of thermal environments. And so they are actually set, and the way that the spacecraft gets to the moon is it's rolling so that we can keep it at a reasonable temperature. And that's balancing the fact that we have the hot sun and cold space, but we don't want it on any particular place all the time. Firefly's doing a great job of building this. It's just fun to see it come together, and we're looking forward to that one launching early next year. Just like cold space, the other thing that we deal with is shadows, and shadows, whether it's on the moon because the moon goes between you and the sun, which is called nighttime, or because we pass behind the Earth in an eclipse, or we go through the backside of an orbit. All of those instantly take away your heat and your input from the sun, and so it allows you very quickly to have to be in a different place. So this becomes a big issue, becomes something that we always want to pay attention to. And I've already discussed planets, so we're there. Charging is an interesting problem for spacecraft just because in so many of the spacecraft, even what we're dealing with, most spacecraft don't really care about whether or not their surface charge is up. So a typical satellite communication or communications satellite, or even something like a SpaceX Starlink doesn't need to worry about whether the outside of their spacecraft is charged up. It's not going to hurt the system as long as they have a reasonable amount to dissipate the energy off of there, and they're not building up a particular charge that they're worried about. That's not going to be a problem. On the other hand, for us, when we're trying to measure charges of the system, of the plasma, and of those particles, if we charge up our spacecraft, we actually affect the science that we're getting. So, charging becomes a really important spacecraft model for a scientific satellite or for a satellite that cares where the particles around it end up. So charging is a unique issue that we deal with. It is something we are contracted to help others with because it's something we have so much experience with and rarely becomes an issue for many satellites outside of the scientific community. In space, the sun is constantly blowing off charged particles, and the Maven spacecraft, we generated lots and lots of these graphics trying to figure out what's happening to particles on Mars as the solar wind impinges on Mars. The atmosphere on Mars is actually ejected by the charged particle interactions. Uh, when these particles come in contact with a spacecraft, they can charge up the spacecraft itself. And since there's no ground, right, you can't just plug into the ground rod that you have at home. It's something that satellite is has to deal with and has to be able to figure out what its own grounding is going to be. The typical simple solution is to actually make the external surface of your spacecraft reasonably conductive. And I say reasonably because if you make your external of your spacecraft too conductive, that often causes other problems with not being able to control currents and not knowing where they're running on your spacecraft. But if you make it just conductive enough, then you know that any static charge that builds up on the system will actually dissipate. This is one of the fun things in separate presentation, but electrostatic discharging between conductive and dissipative is a fascinating thing to watch. We don't want to have the electricity just disappear on our spacecraft. We want to actually control where it goes and make sure that it's coming together into our system. The one place where I don't see that is one of our radio instrumenters really loves gold-plated instruments, and he will do whatever he can to have gold plating on the outside. And that allows us to dissipate the charge off of his instrument and not affect the radio instrument. He's worried that we're going to have small discharges through a dissipating system that are going to cause problems and actually something he'll be able to read in the science of what he's doing. So it causes issues. We try and figure out how to meet it. Like I said in the materials slide, I can do that either by picking a material that's going to dissipate. There are plastics that actually have dissipative properties in them. But most likely, what I'm going to do is pick something that is a metal for my outer shell and then wrap it in a blanketing material that has a known dissipation. And that allows us to control the external surface, but still have the internal metallics doing what they need to balance charging across the whole spacecraft. We will end up monitoring how we mount the different pieces because when you put a box onto the spacecraft deck, you want to make sure that it's actually dissipating. It's not just holding up its own charge. Those can end up in an electrostatic discharge inside of your system or to the lowest potential item that's nearby them. So we don't want that to happen to our electronics. We don't want it to happen from our electronics. Okay, last issue I'm going to deal with today and talk about is designing for radiation environments. Radiation is something that's everywhere in space. It's just to very different degrees. We actually deal with the radiation environment every day. Our skin takes care of it. It's one of the reasons our skin regenerates so much. Thankfully, it's at a manageable level for our bodies. We don't want to have too much. We can get burns. We can actually have problems beyond that. The same thing happens in space. And so what we're trying to do is make sure that the radiation first doesn't destroy the material. That can mean that it's either we can either use a metallic exterior or something that doesn't react to the radiation levels that we're going to see. Every instrument, every spacecraft that we build, one of the first calculations they run is what the radiation exposure is going to be throughout the lifetime of the spacecraft. Most of them what we do is we stay in environments with low radiation. It makes things a whole lot easier on all of us. But some of them we have to go to places like Jupiter. And Jupiter has just an incredibly high radiation environment from the planet itself emanating the radiation. Similarly, when we had the Van Allen probes that I got to work on with the Space Sciences Laboratory, they were specifically made to go into the highest radiation environment around the Earth, which is the Van Allen belts, which are two belts of trapped radiation inside of the Earth's magnetosphere that allow the Earth to deal with particles and the charged particles and how they interact with us. So the problem with Van Allen probes is we wanted to fly and make and see what the environment was like right in the middle of those. So everything we did was based completely on radiation and how to dissipate it, how to shield from it, because really you can't make it go away. You can't make it stop. So what you have to do is try and make sure that you're actually protecting yourself from it. And this becomes an issue for multiple reasons, but the main ones that you will run into is it degrades the material, which we've talked about, and it can also cause erroneous events. So if you think about event upsets inside of electronics, will charge up from radiation. They will then discharge. That will be mistaken by a computer as an actual charge signal, and charge signals destroy your data. Basically, they're false data that you don't want. So there's a constant issue that we're trying to do to make sure that we shield as much as possible. The two main things that we deal with on any spacecraft launch is mass and volume are the limits that we have. Typically, mass and volume also control your costs, so it's, balances out really well, but we're always trying to minimize mass, trying to minimize volume. The problem with shielding is most shielding is mass dependent. So the more mass that you have, the better your shielding is. And so it pushes us to use larger, thicker plates and thicker items and some fun materials that we have as well. So what you can see here in this top right picture is a preamp board inside of the Van Allen probe, which is you can see the main satellite here and its solar arrays, and it has these long wire booms that come out. And at the end of those long wire booms is a preamp. And that preamp is completely exposed, and it's very difficult to shield the whole preamp because you're trying not to have huge amounts of mass, and it's a small system. So what we came up with was the idea of shielding it with a small cap of tantalum. And so this is tantalum, which is a heavy material, has a good high density, higher than aluminum, deals well with radiation. And what we did is we machined a can that would go around the preamp enclosure and would keep it experiencing lower doses of radiation. So we figured out what the radiation dose was that was going to cause upsets in our preamp, and we built a canister that actually would contain that and keep it well. Now you can see there's other components on the outside of this can that we weren't worried about. We were able to get radiation hardened versions of those. So we can actually buy radiation hardened electronics that don't suffer from the same erroneous events. But where we can't get those, we're going to shield. So tantalum was a fun one. The other fun one was the electronics box for this actually had no weight relief in the entire thing. So the box was actually the sides of it were 3/10 of an inch thick, roughly, just a little bit more than a quarter, roughly the thickness of one of your fingernails is wide, and it was solid aluminum. And that was just because we knew if we put enough aluminum there, we would be able to maintain down the dosage that our system was going to see, and it would protect it to the greatest degree possible. We can obviously make it thicker and thicker, but it costs us mass. When we make it smaller, we actually impinge upon our electronics. So what we tried to do is make a single out external system that had the radiation exposure that we wanted. Fun side fact, it was one of the highest resonant frequencies we have to vibrate in order to get ready and test to make sure that we're ready for launch. And this had a resonant frequency of 400 hertz for the entire box. It's unheard of. Typically, we're down in the 100 to 125 range, but 400 hertz because there was just so much material. There was no way for us to have a low resonance. It just was a solid part. It's like we called it the brick, and it completely felt like one when you carried it around. So that's how we protect from space weather and how we design for space weather to deal with the issues of the thermal environment, the materials that we have to have, the radiation environment, and the charging environment that come from being in space. And I'm happy to answer any questions you have. It feels kind of like a fire hose that I've been giving. So hopefully you've gotten something out of it, and I'd love to hear what you heard. Yes, Max Stolarts.
Yeah,
Max,
thank you, Jeremy, for giving the talk. This is really informative. The four topics you went over, how do you normally go about, you'll maybe have a team of people, I imagine. How do you go about prioritizing, let's say that there's thermal requirements, radiation requirements, charging requirements, and material requirements? Like, what's your most limiting factor? What's your, what do you have to specify first before you can specify the rest of the system? I'm curious how, maybe mission by mission, you go about that kind of sequence of priorities or what the critical path is.
that's a
If that makes
great
sense.
question and fun to try and think through because there are so many different answers to it, and it really depends on what the mission is. So if I'm looking at something that's going to go to Jupiter, radiation is going to become a much bigger issue than typically. So right now we've looked at we have a mission that we were thinking about sending to Enceladus, one that we were thinking about sending to Europa. So outer planets missions, and when you're thinking about an outer planet mission, you know that the radiation environment is going to be very difficult and that your time environment is going to be very difficult. You're looking at a 7 to 10 year mission or primary flight before your science mission begins, and everything has to be working after those 7 to 10 years. So the radiation environment becomes incredibly important, and that will play out in how you pick your materials. With a mission like Lucy Knight, where I'm going to the lunar surface, very early on, it became apparent that the thermal design was going to be far more important than we typically give it. And my thermal engineers will constantly tell you that we have them last. Basically, they're going to put a coating on the outside, and so I can completely ignore them and let them design with roughly the idea of what size that box is. And at the very end, I'm going to expect them to glue something on or paint the outside of it, and it's going to be all better. When it came to Lucy, we couldn't do that. We knew from the beginning that we were completely building a mission that was going to be defined by the thermal properties. And that actually got to be more apparent as the mission went on. By the time I got to the end, I would tell you it was completely a thermal mission, and it is defined by the thermal far beyond even the scientific considerations. The scientific considerations were simple compared to that. Then I've got the materials concerns, and materials are nice because we have options, but the material has to do what I need it to do. And so that's where as I'm looking through these different pieces come interrelated. And so that's also, like you were suggesting, or like you were asking, where do they come in? They're all so interrelated. There's something that I'm playing with at all times. I try to get away with not having to worry about surface charging. And that depends on if the scientist comes back against it and says, no, you have to deal with this. So then we can end up with taping the outside surface of a plastic because we needed the plastic for our thermal environment, like we did on Lucy, but we need that plastic to somehow be conductive on the outside and dissipate charge and also have a different radiative property. Those plastics are horrible in thermal for radiation. They actually emit way more than you want them to if you're trying to use them as an isolator. So there's all of these things are kind of working together. It's almost a web. The nice part is, and maybe the hard and the nice part is, I get one piece of material to do all of this. That's the mechanical side that doesn't come into necessarily space weather. But if I look at aerospace engineering and I say, what makes aerospace engineering different for a mechanical engineer? I get one piece to do this. I'm not going to have one piece that is my structure with a thermal part next to it, and I'm not going to have a radiative part that's taken care of next to that. Every one of those pieces is going to work into one part. And so, for a great example of that is Lucy Knight. My thermal isolators, which are going to be out of plastic so I can get my thermal isolation down low enough, also have to be my main structural component, which means I need them to act like a metal engineering wise as far as strength and ability. And I can't have any fractures. I can't have it fall apart. I can't have issues of 3D printing materials. It was the first question I got asked when I said I was going to use a plastic there. They said, well, You can't, because when you 3D print it, it'll fail. And I said, well, that we would never 3D print this as a structural part. And NASA breathed a huge sigh of relief because somebody tried that. But there's all these different pieces that stack up and that I need them all to coalesce into one single design.
That's a nice insight. Yeah. Because I'm in a aerospace capstone right now where we had to basically go through that evolution where we had to come up with when are we designing thermal versus when are we designing electronics versus when are we designing this is for like a little CubeSat. So that's useful. Thank you.
Yeah, and CubeSats are great because they're nice and small, but as you know, you run out of surface area to do the different pieces that you want. And yet you also, because you have such a small space, you have demands on that. You're going to put a solar array on the outside of at least several of those faces. And so it's always a balance of trying to figure that out. It's fun. It sounds like a fun capstone.
Yeah, definitely.
All right, Allison.
Hi. So I I've always thought that the shape of spacecraft are really interesting, because there aren't the same aerodynamic concerns that there are on Earth. So I'm just wondering how these issues that you've been speaking about factor into the actual shape and design of the spacecraft.
It's a great question as well. So most of the shape of a spacecraft is going to be dependent upon the launch, what the structure will do to give the launch environment that we need. Very rarely does the shape of the spacecraft need to do something to deal with space weather. Now, the obvious exemption to that is the solar probe spacecraft, where what you're trying to do is hide everything behind the solar shield, and so everything is built on the taper of the solar cone that comes around this, and what can we hide behind it and what do we need to hide behind it. Other than that, most of what you're doing for shape is transferring loads. So even on solar probe, you can see the cone at the top. What you can't maybe see in my tiny model here is the carbon fiber structure that's actually running on the inside of there that is used to support the shield, because what happens when we launch is this entire model is only going to be held by the bottom, and the acoustic pressures from the launch vehicle are going to shake it. And so all of the mass and energy that is held up here wants to move and doesn't necessarily want to stay attached to the spacecraft. So everything else is built on what does it take to get enough structural strength up to that top surface. Beyond that, typically by the time we can make structural strength, the volume is sufficient. The ability to actually carry the mass that we need to has been taken care of because you have certain pieces that are the heaviest part that you're going to have to deal with. For things like Lucy Knight, the lander has to support itself with all of its propulsion, and that actually is a larger concern for them. They actually have to build enough structure just to support that even though we are a significant mass, we're not enough to completely drive them to re-engineer the spacecraft. And so that becomes kind of the balance that they have. Most of those concerns then come back to the mechanical strength and the volume that they need to be able to put the components in. Does that make sense?
Awesome. Thank you so much.
Sure, why don't you go?
Hi, thank you for taking the time to give that talk.
Yeah, my
Um,
pleasure.
so I was curious about how relief, so like there's I think I've heard of this thing called exfoliation, where like quick changes in pressure lead to cracking at material surfaces. And so I wonder, do materials that you use in spacecraft design, like do you have to accommodate that f for that in a special way, or is that just happen to be a part of the like materials uh like strength, like because it's good for other things? And also, do you, like, when you're releasing the spacecraft, do you depressurize slowly, or like, what's the process for that?
That's a great question as well. So for depressurizing, spacecraft are built to vent. So you actually don't want them to be pressurized. You want that to all flow out. So we actually have rules that we're required to keep enough vent area that allows all of the air to escape without any pressure buildup. And there's a spec for exactly how many PSI. But what I always remember is the number that they give is the volume over the area has to be less than 2,000. So, you take your cubic inches of volume area and you take your square inches of vent area, and the ratio of that has to always be, I guess it's greater than 2,000. So you always want more area, less than 2,000. You always want more area for the amount of venting space that you're doing. And that actually ends up being propagated out through the whole thing. So if you look at a spacecraft and you see the exterior of that spacecraft looks like it's bagged and it's completely blanketed in a solid blanket, those blankets have areas that are engineered into them to allow the pressure to escape so that we're never worried about our own pressure bringing against something, bringing something into the system that we don't want. We do have to worry about the outer layers coming off. Exfoliation is a great way to say it, because that is actually what happens to your skin cells. And when you scrub your skin, that's what comes off. It's what most of dust is. Again, we are our greatest contaminant in space, so we try to keep away from that. For materials, we deal with that more as a contamination and concern that's not so much space weather, but just general material problem and what's going to happen to this material. So if you actually take aluminum and you take a piece of aluminum and you rub it with a clean white cloth and maybe some alcohol, but you just rub it, you look at the outside that cloth after rubbing it, it'll be brown. If you throw that white cloth away and you get a brand new one and you rub it again, and you look at it again, it'll still be brown. And you can do that until you're dead, really, until the end of that piece of aluminum goes away. Because what happens is the outside layer of that aluminum oxidizes so quickly, but the oxide is actually what's peeling off and what's coming off on your wipe. And so we actually do put on surface coatings or passivate surfaces so that we can keep them from doing that, from losing that outer layer, because that outer layer is microparticles that will go somewhere. They will end up somewhere that you don't want them, and we have to deal with that all the time. So that's typically what we're dealing with when we're talking about surface properties and whether or not we can let something fall apart. So the picture that I showed of the palm cylinder with all the cracking on the outside, we would never want to actually fly that, because you have no idea what's happening to the external surface when it breaks open and when it deteriorates enough that it does that. Are you getting particles ejected? Are you actually having the system fall apart? Is it doing what it's supposed to anymore? There's so many different concerns that come along with that. And so what we would do instead is we would either find a way to shield it, we would find a way to protect it and hold it together, or we would find another material to replace that with.
Thank you. Thank you for that answer. That makes sense. I had a quick follow-up
Mhm.
question, if that's okay. Have you heard of the use of biomaterials in spacecraft design, and what do you think about that, if you haven't
So
heard of that before?
I've heard of taking engineered materials and using them for testing, and there are things that we do for using biological sampling. There is We're not currently looking at using biomaterials, and part of the reason is we are very concerned, since we are a scientific institute, we don't want to actually affect our instruments, and we don't want to cause problems with what we bring along. So that would be a concern. I'd love to read more on that because I haven't heard a lot about it, but I think a lot of it is that we end up using materials that are well known and we know what they're going to do to our instruments.
Okay, thank you so much.
You're welcome.
Actually, that brings up a follow-up question, because I've seen we've exchanged emails, Jeremy, where there's great interest now in bioscience in space,
Mhm.
health in space, experiments to determine the space environment and our own health, and on biologics or astrobiology is their bio. And sometimes people come to us and they want to use our shake table, the vibration table, etc. And you're saying no liquids, no liquids, right?
Right.
Especially when there's this chemistry in space. But if SSL got behind a mission of that nature, would you take on the challenge, or would you still be very hesitant to even go there?
Yeah, so there's a lot of qualifiers that go along with that, and a lot of it depends on how we're working on things and what we're doing. So at SSL, we developed the Enceladus Organic Analyzer, which actually is a biological analyzer, where we designed systems that would hold liquid water, and we're transporting liquid water to the outer solar system because it's not like we can pick it up when we get there. So it's a matter of making sure that we can constitute something and we can analyze it. Those are definitely things we do, and the question is more is less whether we're carrying water or whether we have a pressure vessel than what are we doing to make sure that there's no danger from that pressure vessel. And a lot of times that comes down, whether it's a thruster, what have you done to make sure that that thruster vessel is safe when we launch it? And so when we did a CubeSat thruster, thrusters are notoriously difficult to get qualified. And the things that are difficult is because they have to have pressure, or at least cold gas ones have to have pressure. And so to get that pressure vessel qualified is extremely difficult. Well, what I did was I designed it to actually use a DOT certified pressure vessel and open that vessel in space. So the Department of Transportation was responsible for all of my qualification testing. It already came finished, and that allows me to step back and go, okay, I'm already bringing a safe container, and here's how I'm making that work. So I can actually work through a lot of the things that we would like to say, hey, we'll never use this, but that it's not ever that simple. We often can find the exception, and we often work inside of the exceptions of things that we actually need to be able to do. When we run things like the Enceladus organic analyzer, most of it is made out of flexible materials and plastics and even silicones. Well, for most of our science, and especially our optical science, we don't want silicones in the facility. If we could keep them out of the entire facility, I would have been very happy. And we did that for a mission. And at the end of that mission, they creep right back in, and people use them because they're simple and they meet a lot of needs and they actually work very well for what they're doing. But if I look at something like the Enceladus Organic Analyzer, it's made of silicones. And so there's no way we're going to say, no, you can't use that. But what we did have to do is go through and say, all right, here's the stuff that we're really afraid of. There at one end of the spectrum is the stuff we're really afraid of. Then there's the stuff that you're using in the lab grade because you say it's better. And then way over here is the same stuff that they made for space. And there is a space grade alternative. And we're going to take all the processing that you've learned and you're going to relearn it so that we can actually use this in a space application. So that's actually how we ended up being able to build EOA, is to change the materials into something that were reasonable.
I didn't realize that you were helping out with that.
Yeah, that was a lot of fun. I got to manage that project, so it was a
Oh,
blast.
fantastic. Okay, because that was one of the ones on my mind there.
Yeah.
So okay, so you're definitely on board if SSL or one of our customers, so to speak, is saying here's the challenge, you're ready to take it on, which I think
Oh yeah.
excellent. All right. Well, we're coming up on the hour, so we have time for a couple more questions. Happy to entertain those.
I did think of one follow-up answer to what I said for Allison's question about the shape of a spacecraft. The simple example that's easy to see is thinking about CubeSats, right? CubeSats are completely defined by whether or not you can stuff it inside of the launch vessel. And so everything is based on whether or not you can shove it inside of a whatever launch vessel they've given you, whatever your deployer is.
I do actually have a question about launching.
Okay.
So I've heard that a potential goal for future space missions will be to launch instruments from the moon. What do you think is the practicality of that, or like what's your opinion on that?
So launching from the moon is nice because what you do is you get down to a lower gravity environment, makes it much easier to launch. The struggle that we have, of course, from Earth is we have to somehow get it up there in the first place, which means all the fuel and everything else comes from here. One of the things that I personally think stopped us from going to the moon anymore in the 60s and into the 70s and continuing moon landings is there's not a whole lot on the moon for us to use. And so a lot of the materials and the things that we find there are not incredibly enticing. There's not a big lump of platinum in the middle of it, unfortunately. That'd be great. We'd use that. There's not a lot of water ice. There is water ice, we believe, down in the poles, inside of craters, totally likely to be there. But how much? And what are we going to be able to do with that? And if we, use it for human habitation, what are we going to do for, things like fuel cells and things like that that we need to be able to get? And so I think SpaceX is currently dealing with this problem, and they are at the very beginning of dealing with it, of how do we send up just a fuel freighter into space that's just going to carry gas, and then have a gas station to fill our Starship back up so it can get to Mars. Because no matter what we do, we have to get all that mass into orbit. And then we have to either get it to the moon, which means we land it and then we launch it again, or we build stuff in space, which is, I think, why my view of it is why we switched to using the space station. I think space stations are difficult because, one, we put them in low Earth orbit, which means they're constantly trying to fall back. And they're also, we're trying to keep them manned, and manned flight is expensive, and it adds a huge level of complexity. That isn't bad, because we love the idea of going places, and it's like the manifest destiny. Who knows why people struck out across the prairie, but we do. It is something that is built into us. We have that dream of going to the next level and seeing what's next. And so all of those things build together, and the idea of launching sounds incredibly enticing. I see the reasons for it. I'm just not always positive practically how that's going to play out, in the resource management of it.
Do you
Yeah,
think
for
if we
sure.
get
Thank you.
Oh yeah, sorry, Alison. No, I was just thinking, if we get to that stage where we're launching from the moon, people will have to be on the moon, right?
Yes.
There's no way around that, right?
Right. You've got to have a place there first, that you're building something. And this is where things get fun, right? As we start getting into the questions that we're currently grappling with, of how do you mate with spacecraft, and we have enough trouble just mating two spacecraft in orbit, but then how do you get the one that's working better to fix the other one, right? That's a system that our biological systems do great on Earth, but it's really hard to make something automatically do that. And well, it's not impossible, but it's very, very difficult to have it have the resources to do that on its own without carrying something extra.
Yeah, yeah. Which makes me realize that these students are going to probably see extraordinary things in their lifetime that you and I are
Yep.
going to miss out on.
Fun things. Yeah,
Yeah,
there's neat things that we don't even think about, like being able to land the launch vehicles, and we go, wow, SpaceX did something completely new. And it's not that they did something new. They were actually doing that in the 70s. The launch vehicle contractors could land something. The difference is that the electronics that it took to do that were roughly the size of a bus. And so now we can do it in a microchip or a box, and we can land this thing and we can control it to that level with much, much smaller mass hit to the environment of what we're trying to do in the launch vehicle that we're trying to use.
did not know that. Claudia, Phoebe, anything else to add before we wrap up here? No? Okay. Well, I don't see any
I
other
did want to
questions.
ask a kind of like fun question.
Go for it.
Oh, have you seen Project Hail Mary or read the book or anything?
I have not. I'm not sure
Okay.
which one is that.
The new movie that's
It's the same author from The Martian, but it's
Okay.
the new movie that came out, and it's about the guy, like they send him into space to go to another star and inspect like the environment there. But there was so much in the book about like how they designed the like Hail Mary spaceship. So I just didn't know if any of that was like accurate.
Excellent. So, that particular author, when he did The Martian, which I haven't seen or read either, so just so that you can take that with a grain of salt, his research is amazing. The story that he puts together is very fun. The struggle I have in it is because I'm a pessimist engineer. I recognize, you built a character who had the exact skill set that was necessary to take these set of materials and make them work, which is exactly what it would take, right? That's what you have to have. I have a 10-year-old daughter who wants to be an astronaut. And one of the things that we constantly are telling her is she needs to develop more than just one skill. Our astronauts are phenomenally trained. I knew a man when I was quite a bit younger, and he had at least one PhD. He was in perfect health, and he considered that to not even be enough to get in the front door, that he needed another PhD and more experience before there was even going to be an option for him talking to NASA about becoming an astronaut. So it's one of those fun things when you're reading things like The Martian, looking at The Martian, that there's a very specific setup that's going on there that works. And it works beautifully because NASA does use people who are extremely highly trained, and then we come up with crazy ideas and try them. And a lot of times those crazy ideas may not work, but when you're stuck in a situation where that's life or death, you're going to figure out how to make it work.
There
Yeah,
was a
that's
guy named
awesome.
Phil Plate, I think, who used to run a website, Bad Astronomy, that where he would review movies and point out all the things that were either completely wrong or would never actually work. But
Well, it's like the picture that I showed of Lucy Knight where the radiator's in the sun, right? For
yeah,
me, that makes me cringe. For everybody else, they're like, oh, how cute. It's pretty, and I can see all the details that I want to see. There's a model that Firefly is sending around the nation that is a model of our instrument on top of the Firefly lander, but the radiator is over one of their solar arrays.
oh, come on,
Everybody else thinks that that's a great idea, but I look at it and it makes me cringe.
right?
So those are always fun things when you're looking for accuracy in engineering. That's where
Yeah,
you end up.
sometimes aesthetics wins out. Yeah.
Yes, yes. The pretty factor sometimes is a winner.
Well, thank you so much, Jeremy. You're definitely one of the smartest and most generous people I know. So I can't thank you enough. Hopefully, everybody here can join me in giving Jeremy a big round of applause. And you're always welcome back anytime.
You're
Uh,
welcome. I enjoyed it. I'm glad to be here. Glad I could come.
Excellent, excellent. Yeah, we'll be posting this on YouTube as well, so you can look for that on our the Coffee's YouTube channel in the HelioHub playlist.
Excellent.
Uh,
I have at least that amount of technical ability and online presence. I'll go look.
okay, okay, excellent, excellent. All right. Well, thank you, everybody, and we'll see you next time.
Thanks, guys.
Take care.
Thank
Bye.
you.
Thank you, Jeremy.
You're welcome.